Hello everyone, welcome to NS Academy. So today in this video we are going to solve this problem. This is a problem from real analysis first year undergraduates, but we can also say this is a problem of the type ISI and CMI subjective. Okay, so the problem states that let fx be a real valued function, and if for x greater than equal to 1, the function is defined and f1 is given as 1. And we are given that the derivative is simply f dash x equals to 1 upon x square plus fx whole square. And we have to show that limit x tends to infinity f of x, that it exists and the value is 1 plus pi by 4. Okay, so now let's understand this clearly. Fx is a real value function and it is defined for x greater than equal to 1, right? Now let's consider this derivative first. So f dash x is simply equal to 1 upon x square plus fx whole square. Now since x greater than equal to 1 and this quantity, then this quantity x square is always greater than equal to 1 and fx whole square, this is always positive. So this whole thing is always positive, right? So we can safely say that f dash x is greater than 0. When the derivative of a function is greater than 0 for all values of x greater than equal to 1, which is the domain of this function basically, then we can say this is a strictly monotonic function. This is a strictly increasing function, right? And what does that mean? That means that for x greater than equal to 1, we will have fx greater than f of 1. So for x greater than 1, actually we can do this only, because for x equals to 1 the equality holds, and then we have strict equality, right? This thing cannot be 0, so we have a strictly increasing function and not a normal increasing function. Okay, so remember this one, because f of 1 is 1. It is given that f of 1 is 1. Okay. So we will apply the fundamental theorem of integral calculus here. First, remember what it means. A to b f dash x dx, this can be written always as f of b minus f of a. Now since f is a function which is strictly increasing function, so f dash x equals to this, which is greater than 0, we can safely say that limit x tends to infinity f of x can be evaluated. Now it remains to see whether this is finite or not, but yes, it can be evaluated. Okay, now let's see. Using this, what we can do is as follows. Limit x tends to infinity f of x. Now this limit can be written using the fundamental theorem of integral calculus. Imagine this was integrated from 1 to infinity, and if it was, then what would we get? We would basically get f dash x dx, and when it was 1 and this was infinity, you would get f of infinity minus f of 1, correct? But we only want f of infinity simply limit x tends to infinity fx. So what we can write is, if you take the f of a to this side and simply write this, you can write it like 1 plus 1 to infinity f dash x dx. True? Because when you evaluate this, you get limit x tends to infinity f of x minus f of 1, which is simply 1, and they will cancel up and it would basically give you the answer. Okay. Now this can be written as 1 plus 1 to infinity dx by x square plus fx whole square, correct? This is the integral you have. But remember that since f is an increasing function, we can always write that since x is greater than 1, we can write that fx is greater than f1, right? Which is nothing but 1. And since fx is greater than f1, this quantity here should be less than 1 to infinity, since fx is in the denominator, dx by x square plus 1, correct? And if you were to evaluate this integral, the antiderivative of this is basically tan inverse x. Tan inverse infinity minus tan inverse 1 simply would give you 1 plus pi by 2 minus pi by 4, which is nothing but 1 plus pi by 4 as desired by the question. So limit x tends to infinity does exist and is less than 1 plus pi by 4. It is bounded by that value. So this is how we can use the fundamental theorem of integral calculus and monotonic functions to find out the value. This type of questions can come as often as you want. And this can come in both forms, either in subjective form or in objective form, because for subjectives you have to show all this, and even for objectives you need to do all this to find the upper bound, which could be posed as a problem of JEEs. And it has been seen before to find out bounds of functions you are using integral calculus and differential calculus before. Okay, so I hope the problem was clear. Let me know in the comment section if you have any suggestions, and thank you for watching. Please do subscribe the channel.